Welcome. In this video, I would like to present Frequensea, which is a new open source toolkit for visualizing the electromagnetic spectrum. With it, you can do basic visualizations like taking the raw samples and showing them, or doing an FFT visualization, taking IQ samples, but even visualizing in 3D using the Oculus Rift, or connecting various controllers like a Wii controller, for example. The toolkit is itself written in C, and all of the examples are written in Lua. In this video, I would like to show you how to install the software from source, how to build it, and then how to run all of the examples. And I'll finish up by showing you some of the documentation that's available and where to find help. Okay, so the first thing that we're going to do is install all the required dependencies using the package manager. On the Mac, that would be Homebrew. I assume that you already have it installed because it's very useful. If you don't have it already, go to brew.sh and install the package manager. Now, once you have it, it's a good idea to run brew updates first to make sure you have all the required dependencies. Once that's run, it's a good idea to install all of the dependencies listed here. Now, one dependency is not available yet in Homebrew Master, and that is the HackRF package. To install that, what we do is we tap from the FDB Homebrew HackRF repository, and then we can install Brew HackRF. If you have a HackRF connected, you can test if it works by calling HackRF_info, and you should get the information on the board that's available. Once we have our dependency set up, we can download the project source and build it. So we're going to go to the GitHub page, copy the clone URL, and then type git clone and paste out the URL there. Now once that's available, I already have it here, I'm going to type cd frequency to go into the directory. And then, because we're using the CMake system, we're going to have a separate build directory where we're going to build all our sources. So we're going to do make dir build, cd build, invoke CMake with .. to go to because the CMake file is in the parent directory, and then we can type make, and that will build out the source. Now once that's built, we can type /frequency, which is the binary that we've created, and that will show you how to use it. So the most important one is that you can give it a file, which is file.lua. That's in the Lua format, and then there are some flags like VR to render to the Oculus VR. There are actually some other flags that are not documented yet that we'll document later. So to start out with an example, the most basic one that we're going to do is we're going to look at it here. It's just to load an empty file. So an empty file looks like this. It has two functions, a setup function and a draw function. The setup function is called once. There you can load the model, shaders, set up the camera, things like that. And then the draw is invoked repeatedly, where you can first clear your scene and then draw your scene or get stuff from the HackRF or the RTL-SDR device. So to run this, what we're going to do is we're going to type frequency .. for the Lua directory, and then type empty.lua. And that will show you, as expected, a completely empty script, which we can get out of by typing the escape key. Now, a more useful one is the static example. The static example loads a static scene that happens here in the setup function. And then it setups a OpenGL shader using the vertex shader and fragment shader code that you see here. And this code will be visible in all of the scripts. It's a long string, basically, that gets compiled by the graphics card and then uploaded there and run directly on the graphics card, which is what makes it so fast. Then we're going to set up a camera, and finally we're going to draw the scene, or clear the scene and draw the model based on the camera. So let's try running that. And there we go. We have a scene that's built in Blender and then exported as an OBJ file that we now load into the system. You also see that we have an on-key function that gets executed when we press a key on the keyboard. It has some modifier keys, like the shift key, that we can do to, in this case, change the speed, but we can assign them to whatever we want. So by pressing the D key or the A key, we can move this way. W and S move us forward and back. And then if we speed up, we can hold the shift key and then we can go faster or slower throughout our scene. Now, because the draw function is executed repeatedly, we can of course also animate it. So for that, we're going to open the animate camera example. And this is quite similar to the one we had before, only now we have specific code that changes the camera X, Y, Z positions and then creates a new camera based on these positions. The positions are based using sine and cosine functions, and then we use getTime to actually change it based on the time, the current time of the script that's running. So if we run that, we can do animate camera, and now we can see that the camera is animating around the object. There are some flags that we can use here to export this animation. So if we run Frequensea with -- capture, we can actually capture this animation out to files, and it will capture as fast as it can using a multi-threaded system. And that will give you files that you can import in programs like After Effects or FFmpeg to create movies from image sequences. Now, the animate camera is fun because it also can show you one of the basic things that we can do, which is to modify the code on the fly. So the code is actually live, which means that if we start changing the code here, that will actually have an effect on the visualization that's running live. So the simplest thing would be to change the actual model. So that will change the model. We'll change it back. We can change the speed of the animation like this. So that will make it faster or slower, or very fast like this. And of course, we can also change all of the code in the vertex shader. For example, we can say, oh, this needs to be 0.9, which will increase the amount of color that we do. And then maybe we want something that looks a bit reddish or greenish or whatever. The fragment shader we can change as well. So here the only thing we have is alpha transparency, but we can modify or change that as well. So all of these things are just going to be live. And so each time we press save, the whole Lua context is broken down. We run the setup code again, and then we keep running the draw code again. So this is something that might not be obvious from this example, but it means that we can change stuff in setup as well and have that run as we're running the example. A few more examples that I want to show you is the Skybox example. It shows you that we have some of the basic primitives that we can use, and all of them use a similar way of setting up the system. So it always starts with NGL, which is the and N is a name var namespace, and then GL for OpenGL, and then Skybox, for example, -new, and this takes a number of images for the different parts of the Skybox. So if we go through it or we move like this, we can see the entire box actually that this model is set in. And so in the draw function, we do NGL Skybox draw with the Skybox object as the first argument, and then the camera as the second argument. So all of the systems work the same way, and I'll point out how the documentation works later. All of these examples that I'm showing here don't actually have any involvement with the HackRF or the RTL-SDR yet. They're just to show you that this can be used as a generic processing framework or generic animation framework as well. So in this case, the shader is really simple. It's just a grid with points, and we are varying the point size based on the time that we get in from our shader. This one is actually filled in automatically. That's a convention that we use, and so we can play around with the different parameters for time and have it influence, as you can see. Another thing that we provide is draw text. So we have a way of drawing text on the screen. This is a really simple example that just shows you hello world. But of course, because this happens in the draw function, we can also animate it. So we can say random multiplied by 2, and maybe do that in this direction as well. And the last parameter is the alpha transparency. So if we set that to 0.5, for example, it would be alpha transparent. And then we can comment out the clear, and then we can sort of have these things overlap, as you can see. So all of these examples are based on, or don't actually use the HackRF or the RTL-SDR, but the next examples will. So this example, for example, is the first that I want to show you. And what it does is it just takes the raw samples that come out of the device and visualizes them. So it's called samples-tech. And so these are the raw examples as they come in from the HackRF. And one thing that we can do is we can use our arrow keys to go forward or backwards into the spectrum. And we can actually see the frequency change inside of the terminal below. So what's going on is that this works much the same way as the previous examples, which means that it also requires a shader, but then it also has a device here. And so this is the actual thing that makes the device work. So it's set to NRF device new, so N is again our namespace, RF for radio frequency, and then we create a new device that requires 2 parameters. The first one is a frequency that we set it to, and the second one is a fallback file. So if we don't have HackRF or we don't have an RTL-SDR connected, it will use data from that file to actually show something. That's interesting for testing or when you don't have enough device available yet. We create a camera. We have to, because we have to give it a camera in the NGL draw model call that expects a camera, but it doesn't actually, it isn't actually used in the fragment shader or the vertex shader at all. So we create our shader, and then we're going to create a texture. And this is really important because the buffer that we get back with samples from the HackRF is actually sent to the texture update function with the buffer data. So the model is basically just a quad, meaning 2 triangles. So it's a triangle grid of size 1 by 1, which makes it large enough for the whole, to fill the whole screen. And then in draw, we clear the screen. We get the samples from the device by calling NRF device get samples buffer. That gives us a buffer, and that buffer is sent to texture update. So a lot of the code here works with these generic buffers that know their size and the amount of channels that they have, and so we can input a buffer directly into the texture update command. We have to give it sizes. These are checked, but the buffer is basically 1-dimensional, so we have to make it 2-dimensional by giving it 2 dimensions or width and height. And then we finally draw the model. Now the other thing that you see here is the onKey handler, and this refers to keys frequency handler, and that's because there's a special file that gets loaded automatically for all the script, which is called _keys, and that has a list of all the built-in keys with their codes, and then it has things like the keys frequency handler. And this is very useful to have because it automatically takes the shift in the alt key into account, so you can move with bigger or smaller increments. So this one is pretty annoying because it just shows the samples and it's not very useful. A more fun one, I think, is the samples text slow, which is the one set here. And just quickly going to go back to this one. So what this one is doing is the same as before, and I'll show it to you so you can actually see what's going on. That's this one. And what it's doing is going really slowly through the first samples that are available from the HackRF. So the frequency is set to 1. And I think the first frequencies are until 10, there's like test frequencies in the HackRF. And so we slowly progress through these test frequencies. And the way we do that is we have this interpolator that can take buffers, and it has state. So each time you give it or process sample buffers, it will actually interpolate between this buffer and the next buffer. Or it will skip a number of buffers based on this 0.01 value. So if we did make this a bit bigger, then it will switch between these buffers faster, as you can see. Now, these samples are actually not the correct way of visualizing the data that comes from the HackRF, because the samples are actually IQ samples or quadrature samples. I suggest looking at the videos that that the guy from the HackRF, Greg Osman, has made, or Mike Osman has made, to get a basic introduction of how that works. But what I want to show you is how we can take these IQ data and then visualize it correctly, which is by using one as the X and the other as a Y coordinate, basically. And so if we visualize that, then we get something that looks like a circle. In this case, it's not really a circle because the screen is 800 by 600. We can actually change that. So if we call this again, and we say dash dash width is, for example, 800, and dash dash height is also 800, that actually changes it back to a circle. So this is the correct way of visualizing it. It works much the same way as before, only that now we get the IQ buffer directly from the device instead of getting the samples buffer. And then we call texture update again with the IQ buffer. These buffers are always 265 by 265, which is the resolution of the data that comes out of the HackRF. So it doesn't make sense to make these bigger. Of course, you can scale them in the shader, which is what we do here. And then frequency handler keys also make sure that you can move these, but by pressing the mouse buttons or the keyboard buttons. So that moves us through the spectrum. And if we hold shift, we can actually go faster. You can see the frequency changing here in the terminal below. What's interesting is that we can also visualize or hear the audio of the samples as well by using this NRF player device. So the NRF player needs to be connected to the device. It has a demodulation mode, which is basically how we want to demodulate the sound. And then it has a frequency offset, because the RTL-SDR and the HackRF and all of these devices have a big spike right in the middle. So if we tune to the center frequency, we would get a lot of noise. So we have an offset that we use from the frequency. So if we use that, we will hear the radio. It's actually pretty noisy. There we go. The visualization is a bit weird because it's based on shifted frequencies and then filtered, as you can see here. And so the filter is not big enough to actually make a useful visualization. But this, changing this filter resolution to a different value, will actually make it more useful. I can show you. And then we can make the frequency bigger. 101, for example. Now we get a nicer circle. But it's still quite noisy. Now, the noise is not related to this filter because the player itself has an inbuilt filter that we can't actually see or control. That's just available for us there. And then another one that's shown that's pretty standard, I would say, is the FFT. So we go to Lua, FFT.Lua, and then we actually see basic frequency spectrum. The way that works is we have a NRF FFT object that has a width, which is the size of the FFT or the number of bins that we have, and then a history size, which is how much history we want to keep. And then that goes into FFT. These values also need to be the same values, because this returns a buffer. It needs to be the same values than the ones we want in texture update. Otherwise it will look weird. So we get the raw buffers from the NRF device. We send them to the FFT to be processed, so using NRF FFT process. And then we take out the FFT buffer from an NRF FFT get buffer with the FFT object here. And then that gets into texture update. So note that the system is quite the same, only that we have this in between, which actually processes the FFT samples and returns a new buffer that we can send to texture update. And this works pretty much the same way everywhere. Now, in the beginning, you saw a number of 3D things. So because we use OpenGL, we can actually visualize them in 3D as well. There's nothing really special going on about the 3D stuff. It just looks cooler. So these are the raw samples that we saw before, but then visualized using lines in 3D. The difference is not that much. We use, instead of a grid that we used before, we now use a grid with much more points, and then we have a texture that's going to be influenced by the height of each point. So the texture is actually the height map that controls the height. As you can see here, that's the R value here. That's the height of our map. So if we make this value bigger, for example, our texture would be bigger as well. And you can see, of course, it becomes too big now, so we can actually say -2.5 or something to move it down a bit. Again, we can shift through the samples. Another way of visualizing this, instead of using lines, which we said here, using the line strip, we can also do them shaded. This will shade our triangles. And the way that works is because again, we use a texture, we have to calculate the normals, otherwise the lighting is off. So the way we do that is we actually sample the texture 3 times, once in the middle or just the normal position, and then a bit offset to the left and a bit offset to the bottom. And then we combine these, we calculate the normals, which is what happens here. And then we can calculate the color based on a simple lighting function where we take the dot product of our point and the normal and then multiply that by a value. This is the ambient color that we add, so this one would give us more green, for example. And then we multiply by 2 because it looks more interesting, but again, we can tweak this however we want. This is a fall off that we create, so the sides are a bit more blurry. And also here you can change that and you get these circle effects. So note that the rest of the code is actually unchanged. It takes the same device and also uses a camera. It takes a samples buffer, it uses the texture update. So nothing changes, it's basically just the shader that's different. What I think is interesting is that you can also do that with IQ data, and then it looks, that's not this one, and then it sort of looks like this weird circle or pie thing, and then if we shift through the frequencies, we get these really interesting shapes, like these high towers, and there's this sort of rooms that we have as well. I'm not sure if I can find them immediately. This one looks funny. But it's just a fun way of looking at it. And of course, because it's in 3D, we can also rotate the camera and look at it from different angles, things like that. And then a good way to visualize the actual data, I think, is using the Slinky example. And if you saw the HackRF videos, you would also already know what this is going to be. But if we rotate the camera around, we can actually see that we've visualized the sample by offsetting the Z values. So each sample now is a bit further down the screen, and that gives us this nice round slinky-like object. And if we move through the frequency, we can actually see it changing. Sometimes it's very clear that this is actually a spiral that we see. So the way that works is, again, we get the samples buffer, but we have to do something extra. We have to add a position channel, which is using this NRF buffer at position channel. That gives us a position buffer, and that one, instead of feeding that into a texture, because we can't really use it as a texture. Instead, we're going to use NGL model new with buffer. So we're creating a new model where this buffer is going to be the points of our model. And then what we do is use line strip, so we draw lines between all of the different points of the model. And then that happens using this shader, which is pretty simple. It's just taking the position, multiplying by projection and view matrix, so that's the way that we apply camera transformations, and then using that with the point. So that's what we see here. Another fun one that I think is that we can also build some kind of interactivity here, and this is one that we've done using what's called the signal detector. So this visualization actually doesn't show anything up till the point where we start doing something. In this case, this one reacts to frequencies on the 433 megahertz, which is the ISM band. So if I take my keys and I press the button, then you see you get a visualization of what my keys would look like. And I'll do it again just to show you what that looks like. So what we also see here is that we actually have these weird if and WM OpenGL type, and that's because the Raspberry Pi, which we also support, we actually use OpenGL ES instead of the normal or the desktop OpenGL version. So we have to provide two shaders, and they're different enough so that we can't simply automatically convert from one to the other. So for the moment, we have to provide two vertex shaders and two fragment shaders, both for OpenGL and OpenGL ES. If you're not planning on using OpenGL ES, of course, you don't have to provide them, but it's a good thing to know if you're working on the Raspberry Pi, for example. So important is that we use the NRF signal detector here with a signal threshold, and then this is basically built as a state machine. So if we're in the detecting state, we're taking samples, we're processing through the signal detector, and then we're going to get the standard deviation out. And if that's higher than a signal threshold, then we're switching to the capturing state. And then we're going to prepare the things that we can buffer. The reason why we have a capturing state is because the buffer can actually be longer than just one buffer. So we keep capturing as long as the signal is higher than the threshold, which means that we keep capturing I don't know, car keys, or for example. So the buffer gets extended each time. And you see that here by using null buffer append, where we take the buffer that we're eventually going to draw and then add another filter buffer to it. And then finally, when we no longer find enough data, then we go to the drawing state, and there we basically convert that buffer to lines. We update the texture again. We change the alpha value because we want to fade out at some point, and then we draw the model again. And here, if the percentage draw is higher than a certain value, we start fading out, and then we go back to our detecting state, so our first state here. And then the last example that I want to show you is the one that we actually built the whole thing for, which is also the one that we had running on an Oculus Rift, which is the FTC example. And so what that does is and I'll just show you because that way you see what's going on. It basically visualizes the frequency spectrum as C, which is where the name comes from. So at this point we hear radio, and we can sort of go to the frequencies and see the radio signal. And we also hear again from the board. So it's basically bringing all of these things together, taking enough data, visualizing that as 3D, drawing text so you can actually see the text that's appearing, and then with the Oculus Rift, of course, rendering that into pictorial. This one has an interesting function in that we can start going through the whole band, in that works. At some point we'll get into off band, or a little bit off the FM band, and then we get into the unknown, so the colors change. And then there's a tour built in where interesting frequencies are visualized. So if you press A, then you can actually see different frequencies. So this is the tetra network, which is used in Belgium for civil services. We would hear a signal which is encrypted if we hear something. Here we see the ISM band. So again, this is linked to our car keys. So if I press my car keys again, you actually see a big spike where the car keys would be. And this is GSM, for example. Again, we can sort of go through and look at the way GSM is built, or what the signal looks like. And then this is Wi-Fi. So it's pretty calm at the moment. A lot of the Wi-Fi around here is around the 5 gigahertz and not the 2.4 gigahertz. And so we wouldn't see that much here. But we can also just move through and see if there's anything interesting going on. For example, here there's much more data than we saw. So those are some of the examples that we've seen. The FTC example, I suggest that you go through it yourself. An interesting thing there is that it actually is connected to it hosts an OSC server, which means that you can send it OSC data. And on the Mac, for example, we use a program called Osculator to link that to a Wii controller, so that you can tilt the Wii controller and actually move through the spectrum that way, which is interesting if you're wearing a 3D helmet because you can't feel the keyboard or anything. And so that code is all in here. For example, the OSC event is in handle message. And I suggest looking through that and finding out what all these things do. So there's to get started, I would suggest going through the examples. Then there's the API documentation, which lists all of the functions in the different namespaces. So the NWM get time, which we saw, NGL, which is a big one for doing all the drawing. Then there's NRF, which is the big one where you can see how to create devices and how to set up filters and things like that. And then, of course, you can go through the source as well. In C, it's pretty easy to build because you just did it. For example, you can go to nrf.c and then see how all of the devices are built and maybe add your own features and send a pull request. We're open to that. I would send a disclaimer is that we don't actually provide support at this point because this was really an interesting project for us, but we don't have the resources to do full support for that. So if you use it and you like it, that's awesome. But we can't answer too much questions about it or whatever. But please feel free to play around with it, see what you can do with it. If you have something interesting or you want to send us contributions, please do. And thanks for watching.